Our energy diagrams, these can be kind of tricky, but let's look at it. Potential energy is a function of position. Oh yeah, by the way, so this is the beginning of the video. So this is chapter 10, part 3, going through chapter 10, talking about the whole work and energy relationship. Potential energy is a function of position. Functions of position are easy to represent as graphs. A graph showing a system's potential energy and total energy as a function of position is called an energy diagram. Shown is the energy diagram of a particle in free fall. Gravitational potential energy is a straight line with slope mg and 0 y-intercept. Okay. The total energy is a horizontal line since mechanical energy is conserved. So the total, here's this line up here is the total energy of the system. So as we go along this blue line, that means that the potential energy is increasing, and so think of the blue line as the point that you are on the blue line is the amount of potential energy in the system. Well, however close that point on that blue line is to the top line, which is the total energy, the difference will be the amount of kinetic energy the system has. Because the total, between potential and kinetic, since we're not dealing with anything to do with change in thermal energy or anything like that, will equal the total energy of the system. So the sum of them has to equal the total. All right. So up here at the top is where where this blue line meets this total energy line is where the object reaches the highest it can reach for the total energy of that system, unless there's extra energy added to it, unless there's extra work done on it to increase the total energy. All right, here's a particle in free fall in 4 frames. So the object is tossed up. So it's got a positive vertical velocity. It's heading in the positive vertical direction. When it gets to here, it has less vertical velocity than it did because gravity has done work on it to make it slower. Then up here, it has reached its highest apex, so it has no more vertical velocity. And then gravity begins to bring it down. So here it is when it's on its way down, and it has a downward vertical velocity equal to the magnitude of the upward vertical velocity in frame 2. So here we are. Here's our energy diagram over time as well. So here at that time we are right here. The potential energy in this frame 1 is 0. Notice it still has a total energy, and all of that energy is kinetic energy. That's when it has its greatest velocity. So the whole energy there is kinetic. All right, here we are kind of halfway between it, and it's got some potential energy there and some kinetic energy. Here we are when it reaches the top. When it reaches the top, there is no more kinetic energy. It is all potential energy. Potential energy is equal to total energy. And then as it begins to fall back down, we're going back down this blue line, blue potential energy line, and we're again back to a combination of potential and kinetic energy equaling the total energy. And here's the bar diagram, kind of the accounting to keep track of these energies. Beginning, all kinetic, 0 potential. On the way up, some kinetic, some potential. When it reaches the top, 0 kinetic, all potential. On the way back down, again, it's back to some potential and some kinetic. Okay. Shown is the energy diagram of a mass on a horizontal spring. All right, the height of the total energy line is determined by how far you stretch or compress the spring. So you have some outside forces given this system its total energy that will not change throughout the motion after you let it go. Potential energy is the parabola because, and the reason it's parabola is because it is this equation, x minus L naught. L naught is the equilibrium position, equilibrium length of the spring, like it's what it is when you're not stretching it or compressing it. And x is the distance away from L naught that it is. So that's that kind of delta S term that is squared. Potential energy curve is determined by the spring constant. You can't change it. All right, unless you change the spring. You can set the total energy to any height you wish simply by stretching the spring to the proper length or whatever length you want at the beginning of the motion. All right, good deal. So let's think about it. If the spring is at its equilibrium length, there is no potential energy. If you stretch it, if you compress it to the left, then however far you stretch it, then that's going to be at its maximum potential energy where it reaches the total energy. Then when you let it go, that potential energy is decreasing rapidly and changing into, the total energy is not changing. So that potential energy is changing into some other kind of energy, which is kinetic energy. Then when it reaches, as it decompresses, it eventually reaches its equilibrium length. And when that's the case, potential energy is at its minimum and kinetic energy is at its maximum. That's when the object on the end of the spring will be going the fastest. After it passes that equilibrium length, then the spring is starting to stretch. And as it stretches, the potential energy is climbing. The speed is decreasing as it stretches. So the kinetic energy is going down, potential energy is going up. And then when it reaches this vertex here, potential energy is the total energy of the system. Then it starts to unstretch and come back again to its equilibrium position again, and that the process just goes back and forth like that. Shown is a more general energy diagram. The particle is released from rest at position x1. So the particle is released. So it has some. So that's when potential energy in this diagram is at its maximum. Since K at x1 is 0, the total energy is equal to all the potential at that point, at that moment. The particle speeds up from x1 to x2. So the particle is speeding up. All right, when it gets to x2, all right, then it slows down. So because, how do we know that it's speeding up? Because from x1 to x2, because potential energy is decreasing. So if potential energy is decreasing, but the total energy of the system is not, then it has to be changing into something else, which is kinetic. And if it's changing into kinetic energy, then it has to be speeding up. After it goes from x2 to x3, though, the potential energy is increasing, which means the particle has to be slowing down because kinetic energy is converting into potential. Then the potential energy is decreasing again, so it is the kinetic energy is increasing when the potential energy is decreasing. And at x4, it reaches its minimum for the absolute minimum for potential energy, which in this case would be the absolute maximum for kinetic. And then when it goes up here, the potential energy is increasing again, so the kinetic energy is decreasing. All right. When the particle reaches x5, it turns around and reverses the motion. So when it gets to this point, if nothing else happens, if some other outside force doesn't cause things to change, then the motion's going to change. It's going to just reverse that process. Think of it like if you had a ball going all the way up here, then all the way up here, then it just continue on. If there's no friction, it would just continue on. pattern. All right, consider a particle with total energy E2. So the total energy is E2. So this is the total energy line. The particle can be at rest at x2, but it cannot move away from x2. The reason it can't move away is because it doesn't have any extra total energy to move away from x2. So unless some outside force acts on it, it can't increase its potential energy. So it can't move this way or that way. That's called static equilibrium when that is the case. So if you did disturb the particle, giving a total energy slightly larger than E2, like so if you rolled it up the hill a little bit, then it would just roll back down the hill and oscillate very close to the point x2. All right. An equilibrium for which small disturbances cause small oscillations is called a point of stable equilibrium. Now consider a particle with total energy E3. So now consider it to have this total energy E3 now. The particle can be at rest at x3, and it does not move away from x3. This is static equilibrium. But if you disturb the particle, giving it a total energy slightly larger than E3, so if you do some outside work to move it away from E3 on either side of it, it will speed up as it moves away from x3. So it will not just oscillate right there at x3. It will move quickly away from x3, farther and farther. An equilibrium for which small disturbances cause the particle to move away is called a point of unstable equilibrium. So we dealt with static equilibrium in both cases, but in one case it was stable equilibrium, and in the other case it was unstable equilibrium. All right, interpreting an energy diagram. The distance from the axis, so from the horizontal axis to the potential energy curve, is the particle's potential energy. The distance from the potential energy curve to the total energy line at the top is its kinetic energy. These are transformed as the position changes, causing the particle to speed up or slow down, but the sum k plus u does not change. K plus u is always equal to the value at that top total energy line. A point where the total energy line crosses the potential energy curve is a turning point. The particle reverses direction. The particle cannot be at a point where the potential energy curve is above the total energy line. The potential energy curve is determined by the properties of the system, mass, spring, constant, and the like. You cannot change the potential energy curve. However, you can raise or lower the total energy line simply by changing the initial conditions to give the particle more or less total energy. In other words, like stretch the spring more than you did, or raise it higher up from the surface of the Earth. A minimum in the potential energy curve is a point of stable equilibrium. A maximum in the potential energy curve is a point of unstable equilibrium. Okay. Here we have an example. It can be a fairly confusing example, but it'd be better to see it, I think, than not. All right, a spring of length L0 and a spring constant K is standing on one end. A block of mass M is placed on the spring, compressing it. What is the length of the compressed spring? So a picture of that would be like, okay, you have this spring and it's standing on its end. So it's got some equilibrium length based on that. Then you place a ball on top of it, or a block or whatever, and it compresses it. All right, compresses it a certain amount. Okay, so the total energy is going to equal the total potential energy is going to equal the potential energy due to gravity plus the potential energy due to the elasticity of the spring. And so that U total is going to equal. All right, let's look at this this picture drawn by the book here. I want to use the same variables they're using. L naught is the equilibrium length of this spring, but then it's compressed. It's compressed down to a new equilibrium point, which the book is labeling the variable YEQ. All right. So that means that our total energy will be the potential energy due to gravity, which is mgy, plus potential energy due to the spring, which is 1/2 K times y minus L naught squared. All right, let me write that down up here. So it's, what is the potential energy here? If this is L naught, and this is now y. So the potential energy of this block at this point is the mass of the block times g times the height that it is above the earth, which in this case is y. That's what it's going to be called now. And the potential energy of the block on the spring is 1/2 times K times y minus L naught squared. It's kind of like the displacement of the spring, but it's oriented in a certain way. All right. Now, let me show you what this is saying. The total energy of this system is equal to the potential energy of gravity plus the potential energy of the spring. Now, all right, this is what's hard to follow. Here is where that is when the block is at, before it compresses it, when the length of the spring is at L naught. As the spring is compressed, the potential energy due to the spring is increasing, but the potential energy due to gravity is decreasing. And so it ends up here. Right here is where the total energy of the system is at a minimum. It's at the static equilibrium, stable static equilibrium. It's just going to want to oscillate right there. And at the minimum of a graph is where the derivative equals 0. So that's what we're going to do. Take the derivative of that total energy equation with respect to y. Okay. So du dy equals, what's the derivative of this with respect to y? It's just mg. Remember, m and g, those are just constants. All right, plus the derivative of this term with respect to y. All right, the derivative of this term, you take the 2 down front and it cancels out that 1/2 and you're just left with k. And that's times y minus L naught. And then the chain rule says then that's times the derivative of this, but the derivative of this with respect to y is just 1. So we don't have to worry about that. So that's the derivative. And we set that equal to 0 because at the minimum of that, the derivative, the slope of that would equal 0. And so solve for y based on that. K y minus L naught would equal negative mg, and then divided by k, y minus L naught would equal negative mg over k. Then add L naught to both sides of y would equal L naught minus mg over k. And that is the answer they have here. I know that was a pretty confusing problem, so if you couldn't quite understand all that, you're probably in good company. All right, force and potential energy. We can find the potential energy of an interaction by calculating the work the interaction force does inside the system. Can we reverse this procedure? That is, if we know the system's potential energy, can we find the interaction force? Suppose that an object undergoes a very small displacement delta S. During this small displacement, the system's potential energy changes by delta U equals negative internal work, and the negative internal work equals the negative of the force of that work done times the distance, delta S, which we can rewrite as solving for F. So for the force would be F equals negative delta U divided by delta S. In the limit delta S approaching 0, we find that the force at position S is that stuff. So it's the negative of the slope of the potential energy curve. The force on the object is the negative of the derivative of the potential energy with respect to the position. So that might be something to write down. It might help you with a homework problem eventually. The force on the object, F sub S, equals the negative derivative of potential energy with respect to displacement S. Or you could say the negative of the slope of the potential energy curve at that position S. So I could see a homework problem giving you a potential energy curve and asking you to find the force, and you would just find the slope, and it would be the negative of that. Figure A shows the potential energy curve for a horizontal spring with the equilibrium length being 0. The force on an object attached to the spring is that negative kx. Figure B shows the corresponding F versus X graph. The value of the force is the negative of the slope of the potential energy curve. Gotcha. So that slope, the opposite of that slope, is equal to the value here. So this is a positive slope. We have a negative value. Over here we'd have a negative slope, and we'd have a positive value. At each point, the value of F is equal to the negative of the slope of the U versus X graph. Again, sort of confusing. Figure A is a more general potential energy diagram. Figure B is the corresponding F versus X graph, the force versus the position for a spring, I suppose. Where the slope of U is negative, the force is positive. All right, where the potential energy has a negative slope, so it's decreasing, the force on that object is positive. So maybe you think of it like this, like the spring is coiled up a lot, compressed, and there's an object on the end of it right here. The force is positive but as the potential energy decreases. So the potential energy is decreasing as that spring kind of uncoils, but the force up here is positive. All right, then it gets equilibrium, 0 slope, 0 force. All right, and then it's stretched. So the force is this way, so negative force. But potential energy is increasing. It's getting more stretched. Maybe that's one way to think about it. Quick check 1010. A particle with the potential energy shown is moving to the right. It has 1 joule of kinetic energy at x equals 1 meter. In the region where x is between 1 and 2, the particle is doing what? All right, this one should be easy to answer, I think. Actually, it's kind of obvious. Like if the potential energy is going down, then some other kind of energy has got to be going up. So assuming it would be kinetic, the kinetic energy be increasing, and thus the object is speeding up. And that is the case. Alright, same situation. Where's the particle's turning point? Alright, at x equals 1, that's right here. It has 1 joule of kinetic energy. 1 joule of kinetic energy. So it's got 3 joules of potential, 1 joule of kinetic, which means the total energy is actually 4. So the total energy of the system is always going to be 4 then. And we were told before that the turning point occurs where the potential energy line meets the total energy line. So I believe the turning point would occur at 6. That is the case. A particle with this potential energy could be in stable equilibrium at x equals what? Remember, stable equilibrium occurs at a minimum of the potential energy curve. So the minimum occurs, there's a minimum here at 2. So I would choose 2. Alright. The figure shows a particle that can move from A to B, we're talking about conservative forces now, along either path 1, so it can go like this, or path 2, like this, where force F is exerted on it. If there is a potential energy associated with the force, this is a conservative force. The work done by F as the particle moves from A to B is independent of the path followed. So the change in potential energy equals negative of the work done by conservative force as it goes from some initial point to some final point. Now let's read what it says up here. The particle can move along either path from A to B. Force does work on the particle as it moves from A to B, changing the particle's kinetic energy. Alright. If an object slides up and down a slope with friction, then it returns to the same position with less kinetic energy. Part of its kinetic energy is transformed into gravitational energy as it slides up, but part is transformed also into thermal energy because of the friction that lacks the potential to be transformed back into kinetic. Okay, so it's going to have less kinetic energy as it goes because of that friction changing the thermal energy of the system. Thermal energy does not have the potential to go back to kinetic the way gravitational potential or elastic potential does. A force for which we cannot define a potential energy is called a non-conservative force. Friction and drag, which transform mechanical energy into thermal energy, are non-conservative forces. So there is no friction potential energy. Similarly, forces like tension and thrust are also non-conservative. Alright, the energy principle revisited. The figure shows a system of 3 objects that interact with each other and are acted on by external forces from the environment. In the previous section, we found that forces can be conservative. Doing work, W sub C, or non-conservative, doing work, W sub NC. Now let's make a further distinction by dividing the non-conservative forces into dissipative forces and external forces. Dissipative forces like friction and drag transform mechanical energy into thermal energy. Work done by forces from the environment is external work, so that's work done on the system. Interaction forces can be either conservative or dissipative. These do work, W sub C and W sub dissipative or NC. All right. And this is external work also. This is work done on the environment by the system. So this increases the total energy of the system. This decreases the total energy of the system. These things don't change the energy within the system. With these terms, the energy principle becomes this. All right, we've said this before, but you could rewrite it like this. The change in kinetic energy plus the change in potential energy plus the change in thermal energy. Or you could say the change in mechanical energy if you combine the potential and the kinetic into one single term if you want to, equals the change in the total energy of the system which equals the external work done on the system. If the external work done on the system is 0, then there is no change in the energy of the system. That's called an isolated system. An isolated system is a system on which no work is done by external forces. Thus, the total energy of an isolated system is conserved. All right. All this is stuff we've already said. Example 10:10, hauling up supplies. A mountain climber uses a rope to drag a bag of supplies up a slope at constant speed. Show the energy transfers and transformations on an energy bar chart. All right, he's dragging the supplies up the mountain. So that at the beginning, so the initial conditions then would be there's some kinetic energy going on because the bag of supplies is moving with some velocity. He is doing external work. So there's a bar for external work here. There is no potential energy at that point because it hasn't moved up the slope. At the end, there is the final kinetic energy, as it has moved up more up the slope. The kinetic energy has not changed because it's still going the same velocity even as it's higher up the slope. The potential energy has increased though because it is higher up the slope. And if we include the idea of friction, then there is a change in thermal energy as well. How much work is done by the environment in the process represented by the energy bar chart? We just need to do an accounting problem with these bars. So here we have 4 plus 1 plus something equals 1 plus 2 plus 1. So what is that? 4 plus 1 is 5 plus some external work we don't know equals 2 plus 1 plus 1 is 4. So what must the work external be? It must be -1. Move the 5 over. It's -1. That means that the system did work on the environment, transferred some of its energy into the environment. And that is the end of chapter 10. All right, you can look through, pause if you want to, these summary slides. And that's the end. Hope you are going to do well on your homework. See you next time.